When the block is resting on the spring, the net force on it must be equal to 0. That is, its weight must be balanced by the spring force Kx. Therefore, the compression in the spring will be equal to mg by k. For the second part, let us say that the compression in the spring be equal to x at the lowest position. Using the conservation of mechanical energy for the block plus spring system, we can say that the decrease in the gravitational potential energy of the block should be equal to the increase in the elastic potential energy of the spring. That is, mgx should be equal to half kx square. Therefore, x is equal to 2mg by k at the lowest position of the spring. Note that in this case, the spring is compressed by double the amount it was compressed in the state of equilibrium. Note that at this compression, the forces acting on the block are its weight mg and kx from the spring. Using x is equal to 2mg by k, we get the force due to spring equal to 2mg. So at this point, the block will start to accelerate upwards and will again reach this point. In the absence of any friction, the block will keep oscillating like this. Note that at the position x is equal to mg by k, the net force on the block still becomes 0. But the block cannot stop here, as it has attained some kinetic energy by the time it reaches this position. So at this position, which is also the mean position of the oscillation, the block has 0 acceleration but non-zero speed. At the topmost and the bottommost points, the block has 0 speed but non-zero acceleration. This situation is similar to an oscillating pendulum, where at both the extremes, the pendulum has 0 speed but non-zero tangential acceleration, and at the mean position, it has 0 tangential acceleration but non-zero speed. Now, for the equilibrium position, if we write the energy equations from the relaxed position of the spring, the decrease in potential energy of the block is equal to mgx, and the elastic energy of the spring is half kx square. As we know that at the equilibrium position x is equal to mg by k, therefore change in the potential energy of the block is equal to minus m square g square by k, and change in the elastic energy of the spring is equal to plus half m square g square by k. Why is it that the change in potential energy of the block is not equal to the change in the elastic energy of the spring in this case? The reason is that for keeping the block on the spring in equilibrium position, some external force must have placed the block slowly and steadily on the spring such that at each point the net force on the block is 0. Therefore, for any compression x, the block will have its weight mg, spring force equal to kx, and force F such that F is equal to mg minus kx. This force will do a negative work on the system as it is in the opposite direction of the motion. Therefore, the work done by this force will be equal to integral of F into minus dx from 0 to x. That is, minus integral from 0 to x of mg minus kx into dx, which comes out to be equal to minus mgx plus half kx square. Since at the equilibrium position, that is x is equal to mg by k, this force will become 0. Therefore, using x is equal to mg by k, we get the work done by this force as minus half m square g square by k, which is equal to the decrease in the mechanical energy of the system at the equilibrium position. Note that we can also say that if we drop the block on the spring at its natural length, but introduce some friction on the oscillating block, the block will eventually come to rest at the position x is equal to mg by k. Therefore, the amount of energy equal to half m square g square by k will be lost to friction before the system comes to rest.